Good afternoon, everybody. Welcome to this webinar on green engineering. My name is Prof. Manimegli Chetty, and I sit on the Council of South African Institute of Chemical Engineers, and I lead the Hydrogen Interest Group. This webinar is brought to you and hosted by the Academy of Sciences South Africa, the Academy of Engineering, South African Institute of Chemical Engineers, and the South African Institute of Electrical Engineers. I would now like to ask Rajeshri Mahabir to say a few words from the host.
Thank you, Prof. Chetty. Good afternoon, everyone. I'm Raj Mahabir, and I'm from the Academy of Science of South Africa, where I serve as a program officer for STEMI and the humanities. And on behalf of the Academy, I would just like to say that the South African Academy of Engineering is one of our partners, and we as Academy of Science in South Africa is an independent non-profit organization. We were established in 1996 with a mandate to promote and advance science in South Africa. The Academy serves as the National Academy of Science for the country and brings together leading scientists and scholars to provide expert advice on scientific matters and to promote the development of science and research in South Africa. ASSAf's role includes advancing science advisory in priority societal issues, recognizing and celebrating our democracy, as well as converging stakeholders to create a platform for dialogue regarding our democracy and its challenges. So on behalf of the Academy, I would like to say that it's a privilege to be a partner on this wonderful occasion for this lecture, and we'd like to extend our thanks to the South African Institute of Chemical Engineers for asking us to partner with them on this. Prof. Chetty, thank you very much.
Thank you, Ms. Mahabir. Just a very short background. I'm sure everyone's aware about the roadmap for hydrogen and South Africa's drive on the hydrogen technology, and the advances are, some of it is just being done in pockets. So our aim is to try and bring some of the research and to bring the Academy, especially the members of the institutes, and allow them some access to see what is going on in terms of research and in South Africa. So the webinar is a series that we've started, and we hope that some of you will continue to support us in the future. I would now like to introduce our speaker, who is Professor Tien Chien Jen of the University of Johannesburg. Prof. Jen is a B1 NRF-rated scholar with a Scopus index of 44 and over 8,400 citations and a Google Scholar index of 54 with 12,500 citations, highlighting his standing as a researcher known for substantial contributions, and is also published in high-impact journals such as the Chemical Review in 2024, which has an impact factor of 55.8. Professor Jen is the head of the Department of Mechanical Engineering Science at the University of Johannesburg and is the SAIChE chair for green hydrogen in South Africa. Prof. Jen exemplifies sustained research excellence and prolific productivity through his leadership of multiple high-impact research centers at the University of Johannesburg. This includes the ALD and manufacturing research centers. His research portfolio, which accompanies atomic layer deposition, nanofabrication, renewable energy systems, and advanced thermal analysis manufacturing, has yielded over 700 peer-reviewed outputs, including 400 journal articles and 10 books. His success is further reinforced by substantial international grants, NRF-backed investments in advanced laboratory infrastructure, and the establishment of a joint research center with Nanjing Tech University, all of which have catalyzed a dynamic collaborative research ecosystem. Prof. Jen's status as an ASME Fellow and academic of Academy of Sciences underscores the global and national impact of his contributions, confirming his capacity to produce considerably high volumes of influential scholarship. Prof. Jen, thank you for offering to do the webinar for us, and the floor is now yours.
Okay, so is that everyone can see me and hear me? Everyone?
Yes, we can, Prof. You may
Okay.
start.
Yeah, I think thank you. And then I will say a few words before I start my keynote speech. I guess this is an honor for me to join here to give a presentations of I would say that this is probably the first time I present to the Society of South Africa's the institute. I do a lot of international keynote speeches everywhere, but thing is that this is the first time, and I did it here. So I'm really honored to have this opportunity to share my thought of what I have here. And actually, this is I guess this is one thing I can have a meaningful exchange, and then also deliver what I have achieved for my research. And then I hope I can promote more discussion and also promote more collaboration I mean within the South Africa's. And I have a lot of international collaborations with United States, with China. So I think that those are the things we'll bring together. And then I hope that I can really have a strong collaboration with all the South Africa Institute and industries. So I think that for now, I would like to put is that put the word, how to put the share? Oh, here, share. This one, right? Share. Okay, can anyone see? Can anyone see this? See the screen?
Yes, we can, Prof.
Okay, thank you. And then, okay. So today what my talk is atomic layer depositions and green hydrogens empower South Africa's energy futures. And when Professor Chadis approached me and say that you want to talk about want me to talk about green hydrogen, since I'm the South Africa Research Chair for Green Hydrogen. And so I think that's a good idea, because I'm working about two plus years as a Green Hydrogen SAIChE Chair, and also I have a lot of works has invested into it, and specifically tied to the so-called atomic layer deposition. So I guess the thing is that what I want to do is, in this talk, I'm thinking about what is atomic layer depositions. I think a lot of people probably don't know what is atomic layer deposition, even though I know that in the University of Johannesburg, because I have this facility, everybody think about atomic layer depositions. Okay, so I think that is one of the spotlight in the South Africa, because this is only a facility in the South Africa, and this facility probably is one of the best even in the world. Okay, so I think, and then I use this facility to tie this to the green hydrogen's development. So that's how I want to come up with this title. It's moving. I'm moving. Oh, okay. All right. So I think that in the very beginning, so I always, that when I go to the international, go to talk about any talk. Actually, I will always talk about University of Johannesburg. I've been here for 10 years, but I think that I don't know. I really like the Johannesburg, and I'll talk a little bit story when I introduce myself. So I think that UJ is about 50,000, more than 50,000 people, and and coming from about 80 plus countries. And they have currently have a 4 campus, DFC, APK, APB, and Soweto's. And then you can see the one in the right in the centers, and that is called so-called APK. Some of you, maybe that my student or other people have visited that. Another thing is when I first came to the South Africa and I accept the job here, and I go to the APK, this is one of the I would say stunning beauty of the campus. And then in the back, if you see the back structures, it's like a fortress. And I think about this maybe some military school or something, but it's not. So, but I think that I really impressed with this APK. So that's maybe one of the reasons I decided to stay. All right, so the UJ has 7 faculties and the college. So educational law, humanity, art, design, architecture, health science, and the engineering and the built environment, which I reside. And also they have a business school. So, and this is my dean, actually, when I present internationally, he always want me to talk about how good the UJ is. So I think that, well, UJ improved since I came here in 2015. And now they are in the QS World Ranking is 312, which is pretty amazing. In the short period of time. Oh, I forgot to talk about that. UJ is this year is 20 years of the UJ. So, and then the UJ Engineering ranked #1 in South Africa in 2025 by the Time Higher Educations and World University ranking by subject. So that's what I just brief talk about that. I don't need to talk too much. All right, so I think that I will introduce myself a little bit. So that is me. Okay, so I graduated actually in 1993 from UCLA, and I was a full professor from assistant professor, associate professor to full professor and the dean of the at the University of Wisconsin-Milwaukee. And after 2015, actually, there is opportunities, and I was called on my provost, which in the U.S. that's I would say that's #2, and provost, and then he is actually South African, and he said that there is opportunity. Would you like to go there? And that's why I decided to come here for the advanced manufacturing program, and I engage with I think it's, at that time is the 20 years plan of the roadmap for advanced manufacturing. So, and after that, initially I think that I will stay for about 2 years. Actually, that's what also the Johannes tell me. I stayed there for 2 years and come back. And after 2 years, I say I don't want to come back because I really like the South Africa, and especially I can build a team here to do the research I want to do. Okay, so I think that presently I'm the Academy of Science of South Africa, and another one I highlighted is what related to today's talk. I'm a SAIChE chair for green hydrogens, and also I'm a ASME fellow, American Society of Mechanical Engineer fellow, and then I'm the director of Atomic Layer Deposition Research Centers, director of UJ Nanjing Tech Joint Research Center, and there is a latest one is director of the South Africa's, which is UJ, in China is Shandong University Joint Research Lab and on green energy and resource. And I also a distinguished full-time scholars, and I'm a visiting professor from quite a few universities. I think the publications already introduced by the Prof. Chetty. So now currently I have about 70 peer review paper and 480 peer review journal papers. And I have about 32 book chapters and 10 books. And the one that I think that I would like to introduce a little bit is Emergent Atomic Layer Depositions for Hydrogen Energy, which is published by Springer Natures in 2025 this year. Actually, it just published this year, so it's a brand new book. And I think this is to talk about my ASME fellow was awarded in 2011 by the American Society of Mechanical Engineers. So I think that this say that I'm quite a broad field, and then the tubular deposition, machinings, environmentally benign machining, cold gas spraying, fuel cell, hydrogen, and so on. So, and then the I become Academy of the Science of South Africa in 2021, and that was the great honor to be that one of the recognized researchers in the South Africa. My research field, as I say, is quite broad. Atomic layer deposition is a completely new things in the South Africa. So at that time, the thing is, one thing is in South Africa is everything is nice, okay, and everybody working diligently, and then but it's not as fast as when I was in the United States. So the setup, I got the NEP grant from the NRF, but when it started to start, I had to build a facility, so it took a long time. So at the beginning, actually, I said, well, why don't I? Well, and I would like to focus on the simulation. Actually, this started from I was in the United States. In 2016, actually, I got a grant about I think it's 450,000 to develop the ALD process, and that's at that time we already have some base fundamentals for the simulation. So I think that, well, since I just here in I got this in 2016 or 2017, and it's not functional until 2019. Okay, so it's a long delay. So actually, I charged my team to do a lot of fundamental simulation optimization, and for the chemical, especially for the chemical portion of the deposition process. This is a hard one because the thing is in the entire world, actually probably now is only 2 teams are doing that. One is from China and one is my team. So I think those are the thing is we start doing some of the basic work, and this is very important because I'll talk about that, because this is the ALD process is a multi-scale problem. And then we do the product development, solar cell, fuel cell, superconductors, and membrane. We start assembly, and then we are still doing that because for the delay of the equipment available. And I also do the cold gas dynamic spraying. Okay, so I think that those are the things you use the lava nozzles and to accelerate the micron-sized particle to the supersonic state. And you can, because your high impact speed, you convert the kinetic energies to the thermal energies and the melting, and then the coating the surface. So I think those are the one things I spend quite a few time in my careers to do this. And also another one is the dry manufacturing technology, so that specifically dry machining and using the heat pipe technologies. So I think those are the things where one time I think in the United States in about early 2000, and they want to do the because machining is requiring a lot of coolant and cutting fluid, and then they try to do this kind of dry machining and try to take out the fluid, take out the coolant or the lubricants. But this one causes 2 problems. One problem is the thermal management, another is the lubricants. So this one, and I propose the heat pipe technologies to develop this dry machining process, which is awarded by the NSF, National Science Foundation, and over about $500,000. So also I'm doing the solar technologies and solar cell, and actually currently we're trying to develop the perovskite and also the transparent solar cell. I will talk about that later. And the hydrogen generation, of course, this I think the 2 most important part is the hydrogen generation or hydrogen productions, and also the storage technology. And for ALD, actually also can use for the drug delivery and drug discovery, and also is a very good tool for the flexible electronics, and also you can use this to develop and the catalyst. Okay, not only the photocatalyst, you can do the catalyst for even the hydrogen generation. This is my team, and this is probably one of the reason I want to stay in the South Africa, where I was in the United States. I'd like to talk about this. Well, I was in the United States. My team, even though I get quite a few funding, and my team is pretty much 6 or 7 people or 8 people, okay, in the team, and that is the most I can afford. And look at now, I have 20 doctoral student, 20 master student, 18 undergraduate student, and also I have a very strong support from the university that I appreciate, about 10 postdoc. With this team, I can do a lot of things. And I just say that in the United States, here we don't have really so-called overhead. In the United States or in the other places, you have those kind of overhead. For example, the university I was from is 50% overhead. What I mean is once you get the funding, 1/3 of money is gone. And then also you support a PhD student that's worth about 60,000 per year. And so the money you get is much less than what you really can use for research. So that is one of the reasons I think that I want to stay here. And then because here I can use every penny into the research, and that's what I really like. And for the international collaborator, I work with the Penn State, Case Western Reserve, and Purdue. For the Case Western Reserve University, one of my former partner, or the one that I recruit from Berkeley University, is currently at the Case Western Reserve. And we already signed an MOU with them to develop the next generation's batteries. So actually, unfortunately, today probably I cannot talk about any battery. Initially, I put about 20 slides of the battery, but I think that this is not really related to this talk. In China, I'm working with Fudan University, Shandong University. Shandong University is the one we have a joint lab. And Nanjing Tech University, we have a joint lab. And working with University of Science and Technology of China, Northwest Polytechnical University, Shanghai Jiao Tong University, and Harbin Institute of Technology. I have all collaboration with all of them. And the industrial partner, of course, the Pearson is now being eaten by the applied materials. And then we work with Hydrox, which is the one that we do the hydrogen generation, and work with the pits and working with the mitochondria energy. And the mitochondrial energy is developing, I should say, developed the first solid oxide fuel cell in the South Africa. And this is the one we have a long collaboration history. And actually, recently they just donated 9.5 kilowatt solid oxide fuel cell to the UJ, and that's going to be installed as a demonstration. And soon they are developing the 50 kilowatt solid oxide fuel cell, which we'll be using for the other demonstrations. But I think that is the one thing, and I work with them. Actually, we're currently trying to develop the solid oxide electrolyzer cell. So, all right. So the development of first South Africa research, first ALD research facility, and this is the top view of these facilities. So I have two Pearson reactors. One is the typical thermal reactors. Another one is a plasma-based reactors. And I have a clean room, which is an ISO 7 clean room, which is industrial standard. So I think that this is enable us to really, even you want to produce the high precision semiconductors, you can do it over here. Actually, it's the one that is ready for the productions. And also we have a really nice material preparation room. So I think that is the one that we can assembly, first preparation for the assembly of the materials. And the total funding, I think the total funding, including the University of Johannesburg, is about 25 million to set up this facility. And this is two things. One is thermal, the middle one is the thermal base. Okay, is a thermal base atomic layer depositions facility. And you can see that there is you can put the wafer, and then there's rubber on. When you push the button, and you will up and down. And then you can put your wafer, actually you can put so this is very nice, because instead of you kind of only put the one wafer, you can put actually the tool holders, and then you can put I think about 10, 12 wafer all the parts into your tool holders. That means you can do the batch processing. We cannot do the scale up the industrial production, but we are able to produce the batch mode. So I think those are the very powerful one. And thermal is the temperature is actually in about the 150 degree to about 550 degree. So it's the very nice process, a very nice equipment for us to do the deposition. And plasma one is the most expensive one. And the good thing about plasma, actually, every time I introduce the plasma, is because the thing is, because with the plasma reactions, you can actually run the deposition at much lower temperatures. And this is very true for the thermally sensitive materials. Okay, so I guess this can run even near the room temperature. So I think those are another very powerful tool for us to deposit the materials we want. And this is, I think there's some pictures shows that in the finally, actually I think it's 2019, end of 2019 or early 2020. So think about that up to 3 years later. And finally, we can set up the these reactors, 2 reactors. So I think this the left side is our former DVC Prof. Sina, and currently now he's in the New Zealand. And then the right side, you can see that is our dean, and currently is still our dean, Prof. Daniel Michaud. And so I show them I think they give them a kit. Actually, when we deposited the most simple one, aluminum oxide deposition. So it's about, I think one is about 50 micron, and another one is about 30 microns. So I guess those are the kind of very I think that show them that the deposition of this process. Okay, so UJ is very famous for talking about the 4IR from our former VC, Prof. Mawala. So for the industrial 4.0, and then how we're going to achieve the industry 4.0. So there's a lot of things. If you want to do the cybersecurity, if you want to do the robotics, if you want to do the additive manufacturing, and so on, and you need actually do this nano fabrication and using the nanotechnology and use the nano fabrication for the chip and for the other parts. So I think those are very important for you to have those kind of tool. Okay, this tool is a very unique tool, and then we can utilize. All right, so I think this one talk about the Moore's law. Most of people, you know the Moore's law. All right, so I think that what they say is the number of transistor in the integrated circuits doubles approximately every two years. Okay, so I think this is the Moore's law. So I think that's signal that your transistor is more and more. That means your processing speed is much faster. So you can do a lot of computational, and then computational related to the response time is going to be much shorter. So smaller and smaller, smaller than smaller, and smarter than smarter. So getting smarter than smarter. And a lot of function like your in your cell is different than the 10 years ago. I still remember 10, 15 years ago, the cell is so bad. And then a lot of function is not there, but now you can see how much more the function you can have. So I think those are the things that based on the nanotechnology can shrink the size. And as you can see from here, actually also one thing is talk about it. Recently, the people are talking about the 2 nanometer nodes, okay, 2 nanometer nodes, and that the developing to the next generation's chip. Actually, the atomic layer deposition actually is able to create this kind of 2 nanometer nodes because it is the precision of its deposition. All right, so let me introduce what is atomic layer deposition. Okay, so I think this is
Atomic layer deposition, ALD, is the leading thin film technology. You cannot see the ultra-thin films, but you face them in a growing number of applications, usually in global brands that are aiming at superior quality. This is the way the ALD film forms. Molecules stick onto the surface, producing the highest quality ultra-thin layer of desired material. Even nanoscale details of the surface get coated uniformly and conformly with exact repeatability and control. Sun provides the leading
Okay, I guess this give you a kind of like a quick view of what atomic layer depositions, and actually these techniques actually still in the continue to developing for the different materials. Okay, so I think those are the things. Just remember, it's still evolving, and then the more precision and more deposition process can be developed from the atomic layer deposition. So I think that this film already say that is has a superior atomic layer control of film growth. I will talk about why, and it's highly uniform. Okay, those are the one things is the other deposition process cannot achieve, and the conformal thin film of extremely complex topologies and the pinhole free, and also it played a key role in miniaturizations of nanoscale devices and structure in broad array of industrial sectors. Okay, so I think that in the bottom here, I list a lot, but I will talk a little bit more. At the right side here, actually is some of my work, SAIChE solar cell, Joseph junctions for superconductors, and then also the biomembranes, and also the right side, the fuel cell systems. So that is SAAFC system. If you put the more platinum into it, actually it's a crossbreed for the platinum of the PEN fuel cell to the SOFC, and then you can have a much lower temperature operation temperatures. So but that is still in developing. So this is let me briefly talk about what is the atomic layer deposition process. The process that you see in the video is not very clear. So I think that I just give you a quick demonstrations. Okay, this one is the typical we're trying to develop aluminum oxide is one of the major semiconductors. You can see that first you have to pause the TMA. In first, your substrate is been it has been hydrated, and then you have OH bond on the substrate. So you pass your TMA, and once you pass your TMA, then you purge. Okay, then once you purge and you take out the like C2H4 and all others, the CH4, even the CH4, and then you purge that using the inner gas like argon, like nitrogens. Okay, you take out the all the products, and then remember one thing is this is different than the chemical vapor deposition. This is so-called a surface reactions. So it's kind of like you have a lot of reaction site on your surface. Once your surface all the reaction site has been covered, then your process stops. So this has a very unique property called self-limiting. So that's how you can quite precise. So you self-limiting once your everything is being covered, then the reaction on the surface stop. So after you purge of the byproducts, then you start pause the another reactants or precursor, and that in this case is H2O, water. And once you have put the water, and then you have byproduct, the CH4 and others, and then you can purge that outside your reactors. So you can see from here, it's very intriguing. So you can have one layer of aluminum oxide. So you continue repeat this process. So this is considered just one cycle. So you can continue repeat this reaction cycle. So you can have 1 layer, 2 layer, 3 layer, as you can see from there. And each layer for the aluminum oxide is around the 0.9, well, depends. Okay, so sometimes more, sometimes less, depends on how this, but typically is about 0.99 Armstrong. So I think that now you can see it's below the nanometer. So I think those are the thing is 10 Armstrong is 1 nanometer. So I guess you can have this kind of precise depositions and to create the thin film you would like to have. Okay, so this is the lot of industrial application and still developing. And so you can have NAMs. Okay, you have MOEMS, optical scanner, and so on. And then the passive electrical devices. And you have thin film magnetic head. And also you can create a nanoparticle, nanomaterials, and porous object. And here actually is I'm pretty much get into the most of the field. And the lithium-ion batteries for cathode anodes and solid state electrolyte, and then the membranes. Okay, so I think that this is for the separations and prevention, environmental pollutions, water purification and gas separations, hydrogen production, purification and storage, and develop the deposition of the catalysis, and then the fuel cell, porous organics membranes, and energy storage, which is the you can do the lithium-ion batteries and also can do the hydrogen. So and the photocatalyst, solar cell, and a lot of, and so on. So I guess this is this actually that's one thing I like to say is this enable me to do a lot of work for the atomic layer depositions, and then so with this I can do especially when I talk about these hydrogens, and then I really has this ability to do the a lot of work. So introduction to atomic layer deposition research and development in my research group. All right, so the first things, okay, we talk about the purpose of research and development. Okay, and this one thing is very important because we're trying to develop the device or the film, whatever. You want to be in the nanoscale because you want to have those kind of property of nano properties, material properties, and these properties, you know that in the nanoscale is very different than for in the box scale. So nanomaterials, the development of nanomaterials, and I'll talk about that, and then the nanostructure. So ALD is one of the best tool. You can develop your nanomaterials. Look at this way, all right? Just look at this way. I always talk about that. In the reactors, because you are doing 1 layer at a time, and then you can put a different precursor into your reactors, so you can create a functional layer of functional materials, and based on the nanostructure or nanomaterials. And that's very important because the thing is now you can tailor whatever the material property you want. Okay, and then you can layer by layer to deposit the material and to achieve your properties. Say, for example, mechanical properties, the chemical properties, electronic properties, material property, and so on. So I think those are the very important things we should recognize, and also it can create a different type of nanostructures. Okay, so an LD is really a very versatile tool. In the bottom, actually, when I first get the LD, and then one thing is very important is reactor design. Actually, this is one of the patents by all the company, and different reactor has a different abilities. But I think that very importantly, you need to be able to do your reactor design. Actually, we do a lot of simulation and we do a lot of work in the reactor design. We try to see what is the best performance for the reactors. So because it can affect your deposition properties, and it can and then you can change the geometries, what you want to deposit, and also all the properties, mechanical properties. And another one is the most important is the chemical reactions. So I think the product result would depend on how your surface reaction and then the thin film you have created. And so the recipe design become very, very important. And the recipe design actually will change the entire property of the film you deposit. And finally, you can use this kind of chemical reaction to optimize your deposition process. And the defect analysis, actually, you can control the defect study. And actually, the one thing is in this, when we are talking about that, we are talking about when I work with the University of Science Technology of China, and when I visit them, and he's so happy. Actually, I will talk about another one. And then he said that if you can create a defect, and then you put the one flattened atoms on the defect, and the reaction rate is about same. But when you put the second atom into that on the top of it, and your reaction rate increased by 88%, 88 times. I'm sorry, not 88%. Reaction increased by 88 times. And then you put the number the third on top, and it becomes unstable. It's very intriguing. I saw that result. So I think there is something we can play around with that. And finally is the product design. So you have a thin film creations. Okay, that's the most important part for this ALD process. So I think and then we are looking for all the industrial product fabrication, like what we are doing for the green hydrogens. All right, so I think I always talk to my student. Okay, so you are the one to determine what you are going to get, right? So in the ALD process, as I say, the best one is you can generate actually the new materials or functional materials catered toward the function you will need. Okay, so but how are you going to deposit? You cannot come to I think a lot of students come to, Prof, I want to do this, okay? But it's maybe it works. And then you want me to do the deposition. But I don't know whether it's working or not. So I typically what I want them to do is tell me whether it's going to work, okay, using the numerical simulation. As I said to you before, I'm probably only 2 teams in the world is doing this simulation, okay? And this simulation, unfortunately, is across the multiple scale, okay? So I think that we need to do actually, I put it here, DFT, MD, and CFD, okay? So at the right side is from one of my book a long time ago. And actually, you can see there's 3 scale, microscopic, and the mesoscopic, and the macroscopics. So how are you going to do the deposition if you want to know the growth rate? Okay, so and then the scale actually is across all these 3 scales, depends on your Nusselt number, or from large to small. Okay, when the Nusselt number is small, that means you can use the continuum. So that means the Navier-Stokes equations, conservation of energy, conservation of species, and so on and so on. So I think those ones you can do those kind of simulation. But actually, the real reactions actually is in the molecular level. So you need to do that kind of like molecular dynamics. And the interesting thing is, you do the molecular dynamics, how are you going to implement your microscopic scale into the macroscopic scale? Okay, so this is still a challenge. And then so for the LD, actually, I have one paper in lattice Boltzmann, which is the mesoscale, but I don't like the result. So anyone, if you are interested, working with me for this one, and I will be really interested, because this is a quite challenging problem. Even in the Penn, when I visit the Penn State, I challenge them at the same problem. Anyway, so and I'd like to talk about the CFD, that part. Actually, that one is a very intriguing one. Always like to talk about this. I visited the University of Science and Technology of China, which is a top 5 university in China. And there is a Professor Lu, who is an expert in the atomic layer deposition. And he went back to China from the Argonne National Lab. And he is the one of expert in the ALD process. And so he is actually manufacturing his personal ALD reactors. And this is the GEMSTAR 6. This actually is the GEMSTAR 6 reactors for the catalyst development. And then he dragged me to his, one time I visited him, he dragged me to his office, his lab, and showed me this GEMSTAR 6 reactor. He said that when you put the reactors, okay, for the operation, and then they found that it's the the non-uniform, because I think the one thing is ALD is the good for is uniformity. And you say that you always see a thicker layer or the stripe on the top of the wafer. He doesn't understand why. And then he want me to kind of do some investigation and using simulation. He should know that I'm doing a lot of simulation. The reason why, because he doesn't know. Actually, you can see on the top of that CFD, you can see there's a manifold. Okay, 4 on the left side, 4 on the right side. What they do is they are putting the 2 precursor. So one pulse and another one. One pulse for different precursor, and then the purge for A manifold will both push the inner gas out. Right. So I think that is the original design. And then we just do we actually based on there and we do the simulation, and very strikingly, we saw that actually we published in one of the journal, and that you see on the top of the wafer there is a very thick layer. Okay, there is a very thick layer, very interesting. And then they're asking me, can you kind of redesign and see whether it can be improved? And actually, then I suggested that we can do a slit. So you can have a 2 slit and then the rectangular channel, and then you can do the similar things. And we do the simulation again. It shows that yes, the thick layer of the deposition actually has been nearly eliminated, a much smaller difference. So, but actually, anyway, so this is some of the work we do together. And so I guess that this is one I always tell my student, before you go to your say that probe, I want to deposit using ALD. And then because it's very expensive, all the ALD, unfortunately, this is one part. It's slow and expensive. This is the disadvantage. So I tell them that before you do that, go through your first intuition based on the DFT. Okay, so you can know that whether this from the first principle, whether your materials does work. And after that, we can go through the MD and CFD for do the verification. Okay, so in my group, we do a lot of experimental study, okay, in the bio and nanoporous membranes. Okay, one of my PhD students now is in the US. Probably, I don't know he's listening to this one or not. And so using the nanoporous, and another one is this one I really want to do is the biomembranes, but unfortunately, none of my team member want to take over because they think it's too tough. Anyway, so flexible electronics. Okay, so I think that this is one of the best tool because you can deposit those kind of the flexible electronics very easily, and you can utilize in the flexible electronics solar cell. So the right side is peroxide, and then peroxide, and also you can see the bottom that is a transparent solar cell. Okay, I think that we are currently working with the MIT developing this the transparent solar cell, and actually I already have one right next to me. Actually, I cannot. Maybe I can show to you, but this is okay. But anyway, so it's a transparent, okay, transparent solar cell, and but we are still trying to get the better result because you can see if you can have a transparent solar cell with the performance similar to the typical solar cell, then you will have a huge market for that. It's not easy to develop. Then the catalysis. Okay, so we are good at ALD can develop the catalyst very easily for deposit on the surface you want to. And fuel cell, okay, PM fuel cell and electrolyzer, and then we also use this to develop for the hydrogen generation. Electronics, and you can see that this is one of the major advantage for atomic layer depositions. You can see in this kind of so-called trench. Okay, this is a trench, which is the most difficult one for deposition process. You know that you use a CVD, PVD, whatever the physical vapor deposition or chemical vapor depositions. When you have this kind of step change, and you will have a problem with the trench, the hole, because you are going to block the block the hole, and then you need to do either the etching process or other process to create to cut through the hole. So I think those are the nice features that the ALD can do. You can see in this figure, they deposit really nicely without further processing. Wear protections, okay, of course you can deposit a very thin layer, and actually we're also doing the anti-fogging process and developing the anti-fogging and for the development, and then we are still ongoing, but we have some result. Drug delivery and drug discovery. Okay, so ALD typically we are working also with the and one of our DVC is DVC is working. She is working in this area. So we are ALD actually is one of the tool that can coat the nanoparticle or larger size and do the single drug powder particles applications. So I think this can be used in pharmaceuticals formulation. Or the funny part is, I would like to say, funny part is when I have ALD, the ALD centers and the research centers, and then with that, they thought if we are going to develop, we are developing the pharmaceutical tool and pharmaceutical devices or something, and the medicine, and then so they do a similar for the pharmaceutical. And if you have a chance, I can show you that. Okay, so I think those are the lot of application. And then okay, so now talk to my my topic. So hydrogen generations. Okay, so you can using this to do the either the solar hydrogen generation or the one that the green hydrogens generate by the green electricity. So this one thing is so-called membrane electrolysis devices. Actually, that's what we are currently developing, and that is working with Hydrox and the hydrogen storage. Okay, so graphene hydrogen storage with palladium doping, so you can storage the hydrogens within these 2D nanostructures. And currently, we also approve that yttrium doped decorated morphine enhance the hydrogen absorption capacity a lot, and then also exceed the target of DOE target of 5.5% weight percentage. So I think, and then we'll talk about more about that. So, all right. So I think that also the good for the sensor, ALD for the sensor, because it's a very thin layer deposition. So I think that's naturally is very easy to understand. They can do a lot of depositions for the sensor, and I think the right side is the lithium-ion batteries, and I think this is the one currently we spend a lot of time doing the next generation lithium-ion batteries. So I guess this one is a lot of applications. So electric hybrid cars, and the portable electronic device, aerospace application, big scale energy storage systems. So I guess recently our breakthrough is using the niobium doped the lithium-ion batteries. And it's funny part is in 2024, end of year of 2024, there's IMECIS, International Mechanical Engineering Congress and Exposition, which is the largest one for American Society of Mechanical Engineering. And then actually they invite the Nobel Prize winner. I forgot. He was from New York University. And then the interesting thing is last year, and he did his keynote speech, and he present his work. Okay, he present his work. He is going to using the he present that he said he's going to use the niobium doped for the material for the cathode, right? For the cathode, and then so I think those are their new development. And unfortunately, I just say unfortunately, is actually what happened is we already done that in 2 years ago, 3 years ago. So is actually one of my students' PhD thesis. So it's kind of very interesting. So currently we are working with some of the domestic company, and also we are working with the I just said to you before, Case Western Reserve of the spin-off, which one of my partner before, and doing this next generation lithium-ion batteries. All right, so let's talk about the emergence atomic layer deposition for green hydrogens. Okay, so I think that again, we want to do as how it's going to do this one, and I want to through the theoretical simulations and then also through the experimental design. All right, so I think that we select the different materials. So for electrocatalyst materials and also the storage materials. So electro, that one we are using for the hydrogen generation, and storage materials we are using for the hydrogen storage. Okay, so we are going to, as I say, we want to through the DFT, MT, and CFT simulations to know based on the first principle and also the reaction, MT reactions, then we can know whether it is feasible. I want to know whether it is feasible from my student, because my student have a lot of nice idea, but the thing is they don't know whether it works. So I want that to prove, even though it take a little bit time, but it's not very long, a couple months. And then the experimental design, so we can use the electrolyzers, electrofabrications. Okay, it's take a long time, especially when we do the depositions. In a lot of situations, we need to build this electro material, for example, nickel irons, and we struggle quite a few times to finally be able to develop the nickel iron. Why nickel iron? I will talk about that. And then also molybdenum sulfide is another challenging for us, because I wasn't able to get the H2S and from the South Africa. But anyway, so there's a lot of difficult things I'm facing, to especially this will not happen in the United States, but here a lot of materials. And when I want to get it, and I face a lot of challenges, because we are doing a quite cutting edge research. And substrate is nickel, titanium, stainless steel mesh, or carbon papers. We are using the LD. We also have the CVD, and so that when we want to do the much thicker layer, because there is a lot. So this is a kind of complement to the LD. LD is a very precise, very thin, and then you take a longer time to do. So I think that's LD and CVD, and also we can do the spin coatings. And then after that, we do a lot of characterizations and do the performance evaluations. So this is kind of like a method and the design, that process. This is one of the numerical studies for the hydrogen generation, because we don't know which kind of catalyst, which is the best for the hydrogen generation. So we are using the reactive molecular dynamics, called RMD calculations, and to analyze the key step of reactions of alkaline hydrogen generations, evolutions, reactions. Okay, so we use a lot of different catalysts, nano surface, nickel and platinum. So okay, the thing is, when we work with Hydrox, the company we work with, and then the boss, the CEO say, why don't we just use the platinum, but the platinum is the most expensive. And that is, we should avoid. He said that they suggest maybe just use all the platinum. But I say that, well, that it's going to be very expensive. We can reduce the cost by just coating the thin layer, but it's not a feasible way. But anyway, so we say that let's do some simulation. So I have this surface is nickel oxide and nickel irons composite, platinum nickel composite, and iron nickel platinum composite, and iron nickel oxide. So I think those are things that we do this kind of reactive molecular simulation, and this gives us a kind of intuition and idea of what is the best one. It's very intriguing. So here, this is ABCD, but we just look at the simple one. Okay, so the conclusion in here is, you can see all the diagrams. You can see here is nickel irons. The performance of nickel iron is better than nickel, and better than platinum nickel, and better than nickel oxide. So I'm not saying that this is 100% correct, but the thing is that this gives us the first intuition. Okay, say that, oh, nickel iron actually give us the best performance, which is wonderful, because you think about platinum is so expensive. Okay, if we can get the nickel iron and but also nickel is good. And actually, there's a lot of alkaline the hydrogen generation actually did use the nickel, but we found the nickel iron actually give us the best performance. And this one is that we are trying to see whether what the nickel iron and nickel iron platinum or the nickel iron oxide. So you can very quickly see nickel irons on the right side is better than all other two diagrams. So there, look at the number 350 on the most right side. Oxide is good. Oxide has some problem, and then the nickel irons platinum. So and then you can see the right side is at the 450. So nickel iron actually give the better performance, and actually we found the nickel 2 iron actually give the best performance for the hydrogen generation. And this shows that, well, this is nothing special, but this shows the higher the temperatures actually give the nearly give you the best result. So for the nickel 2 iron. So I think those are the things shows that we already at that time we think the nickel iron composite should give us the best performance. So we do an experimental study, and then we deposit and using the ALD process, and we annealing it, and then so we do the water splitting, the alkaline hydrogen generation. You can see that one in the water splitting. That one is one that currently reside in the hydrox, and there's much higher power. It's 1.1 kilowatt, and then we can record the result. Actually shows a quite similar result we have. And this is another hydrogen generators instrument. So this is actually the one that commercially available, is about 20 kilowatt. And so I think this is the one that we're trying to kind of move to our facilities, because UJ, I think that want to have this facility for the next generation development. All right, so we have some equipment in the left side. You already see that is LD equipment, and then we also have CVD, and then we also have hydrogen generators equipment. And right side, top right, is the one thing actually the fuel cell and electrolyzer demonstration facilities for education and training. I think that this is a very important one. Why I'm saying that? While I was visiting in the China, I went to one of the university, and in one of the China, I give a talk, and then we have a dinner, and their vice dean of engineering, and kind of sit right next to me and start talking to me. And he said that he doesn't feel that the fuel cell or electrolyzer is going to work. Okay, he said that we don't have water. I don't want to use the fuel cell. I say why? I say you put the water in. Actually, in the fuel cell, you put the water in and you get your water back. Okay, and you put the hydrogen in, you get your water back. And you can recycle it, and then regenerate the hydrogen, and you can reuse again. All this is a process. Okay, so then he kind of backed down, and then he next things he tell me is, but the fuel cell. He thought the fuel cell is like engine or combustion engine or those kind of power generator. It's going to be very noisy, like a diesel engine. I said no, sorry. Fuel cell doesn't create any noise. It's just be very quiet. So then I kind of funny is I see tons of people right next to me, and that's from industry, and then from Chinese industry, they kind of all listen to me. And but I think that's the one thing I feel like this will be very useful for the demonstration. Actually, I think that especially when the people doesn't really understand what is a fuel cell, I think that still is poor. And also electrolyzer. So what is electrolyzer? This actually really can help. And the bottom, this one, I'm going to go to the next one. And this is the because I think this electrolyzer, the 1.1 kilowatt, is too far away from the UJ, is in the hydrox. So I think that we decide to build a smaller one, okay, smaller scale. And this is a calculator that's about 44 watts. And then this is a small one. And then we can use this to quickly sit right next to my ALD research centers, and we can develop the catalyst and put right into it. And that's much easier for us to develop the catalyst for the process. All right, so I think again, for the hydrogen generation using the so-called DEFT technology, which is membraneless. Okay, so this is the basic concept. Is the cathode, anode, and then you have the cathode and anode materials, and then you kind of like porous material, and then then you can have KOH water into it, and then you can have hydrogen and oxygen splitting. So this is give you a kind of very clear indication how this is processed, how this process is working. And we don't have I checked the literature. There's not many I think that there are not many, some experimental work as well, and also the simulation, numerical simulation. So I think that I charged my team actually recently. I say, why don't we understand how DFT is working, and then we can do the simulation, and also we can optimize the process, and maybe we can apply this similar to PM and SOEC. So I think those are the things that we are currently developing. So this is lab scale alkaline DFT electrolyzers already set up. And then we're doing the CFD models, and then we're buying the console. So there is a simple demonstrations, and actually this is shows pretty good result. And so I think this is the one that the initial, but I don't want to show the data because it's not complete yet. But I think this is the one thing we are current to do, and then we're trying to develop our next generation alkaline, the hydrogen generators. All right, so there's some work. There's some work from my publications. So this one is from the Journal of Energy Storage Enhancement in the Hydrogen Storage Capability of Borehole through the yttrium dopings. And of course, this is a theoretical study for DFT result. Actually, this result shows that yttrium doped borehole can be a promising materials for hydrogen storage. And then we through the geometrical analysis, and then we found that the 6 hydrogens molecules can be absorbed by over yttrium doped borehole. And also when we calculate this meet the requirement of US DOE target for 2025 is 5.5 weight%. Actually, they have I think they have the latest shows that the optimum they want to 6.5%. That's mean the futures. Another one is a thermodynamics energy analysis, and we find that the hydrogen absorption energy is in acceptable range, is minus 0.133 EV to minus 0.17 EV for the stable hydrogen storage. So this is another very positive result. And then we further do the electronic analysis, and we found that it shows the good electronic properties and a good charge transfer directions. Then we do the MD simulations, and then we see the great structure stability and H2 desorption performance even in the room temperature. So I think this is very important because you want absorption and then the desorption. So I think this is and also especially in the room temperatures. So I think this is what I'm saying is from the theoretical it works, but I think that at the end of the day you need to do you need to develop the materials. But I think that we still have some challenges. We are doing that, but we haven't really got the final result yet. Okay, so this is another new study for the absorption of hydrogen on lithium, yttrium, and zirconium decorated boron carbides. And this one is a secret one, and we we want to, if we successful, we actually doing that, we successful develop, we want to patent this technology. So this one. So in this here, this kind of decorate boron carbides, and the bond length of the hydrogen to hydrogen range from 0.74 to 0.76, 0.75 to 0.79, and for yttrium and zirconia. And the maximum absorption energy is minus 0.188, minus 0.296, and minus 0.275 EV for the lithium, yttrium, and zirconia. And I think that the most important thing is, I think the highlight in the center is each lithium atom can capture 6 hydrogen molecule. And then while yttrium and the zirconia atom can capture 5 hydrogen molecule. So if you calculate the weight density, and it's come out with 13.4%, weight percent 7.3%, and 8.1%, all exceed even the U.S. Department Optimate U.S. Department of Energy is 5.5 is 2025, 6.5 is ultimate. And this is one work actually for the chemical reviews. And actually this research review reviews the current state of art of advancement in called electrolysis of the CO2 H2O and in solid oxide electrolyzer cell, SOECS, to produce the importance of syngas intermediate. And this overview of it shows the latest research on the operating principle and thermodynamics and kinetics models are included for both oxygen ions and protons conducting SOECs. And advanced materials that have recently been developed for both type of SOEC and summarize. So I think those are one of my latest, well, not latest, but last year's work. And this is another one. Actually, when we try to come up with these papers, this published in 2023, is we think about solid state hydrogen storage is aimed to store hydrogen in a solid matrix and offering potential advantage, okay, such as high safety and improved energy densities, and compared to the traditional storage methods such as the compressed air or liquid hydrogen. So in these reviews, borrowing nanomaterials and chemical and physical properties are discussed and related to the hydrogen storage and binding energy. So I think this is just a review that we come up with. This is another work in the International Journal of Hydrogen Energy, so effect of palladium's nanoparticle decoration on hydrogen storage capacity of beta-12 borrowing. And this also shows very good, they can bond up with 5 hydrogen molecules, and then the acceptable, I would say acceptable absorption energy range from minus 0.108 EV to minus 0.234 EV for reversible hydrogen storage. So I think this is shows actually this shows pretty much in the part with the DOE target. And this is another work, but this is for hydrogen generation. We published in the International Journal of Hydrogen Energies. So this is theoretical insights of electrocatalytic hydrogen evolution of molybdenum phosphate nanocrystal. Yeah, so I think those are the one work. Actually, this shows that the hydrogens give free energies of absorptions. Shows that the HER activity ranging from minus 0.35 to 0.10 EV. So which is also quite a good the free energies. So I guess this is one work I think that we can play around. Actually, is to have better hydrogen generation. Another thing is I'd like to talk about this book. I think that advertise a little bit. So Yeah, this is actually this is a book published with all my research team, and published in January 2025. And Peter Oviro is a leading author, and he is currently in the United States, and the Sunday Oimbo is also in the United States. It's very strange. All my students go to the United States. So yeah, and the Oimbo is currently assistant professor at University of Texas. And then the Sina Katanzade is also currently is my SAIChE postdoc. And Patrick Imosili, actually he is currently a senior lecturer, also my former postdoc, senior lectures in the at my department. Okay, so I think this book, I think that we try to talk about, because nobody talk about this, because we are the only one developed have a atomic layer deposition. So we are in the perfect positions to write this book. Okay, so I think that this book cover a lot of materials. So we are trying to provide insight into the use in advanced nano patterning for microelectronics, energy storage systems, desalination, catalyst, and medical field, and so on. So we have a lot in provide offers in this book. And yeah, I think that if you like it, you can kind of order the books, or can come from the library. All right, so I think the next one, I'm going to talk about transitioning to a green hydrogen's economies. Okay, perspective on the South Africa. So I think this part is all tied together. So I think this part actually is one of my keynote speech, international keynote speech last year. In the one of also is chemical engineering, the international conference. I think first let's talk about South Africa's energy landscape. Okay, so here we can see that at the bottom there, you can see creating a cleaner and more efficient ecosystems. Okay, so I think that is the center of that the circle. And then the first one is the national electricity market. So if we look at that, and that means that it's been developed to open up electricity trading, allowing multiple producers and buyers to participate. This helped create the competition, reduce costs, and improve the service delivery. Next, for the open access energies, ensure that all energy producers, including the small renewable projects, have fair access to the national grid. And this encourages investment and innovation across the sector. For the project energy connections, focus on the strengthening regional and the cross-border transmission links, improving energy reliability, and enabling the sharing of power between province and the neighboring countries. And for the renewable energy sources, highlight South Africa's commitment to clean technologies, and such as wind, solar, and hydropower. This shift not only reduce our dependence on the coal, but also help out carbon emissions and create green jobs. And for the Energy Pro plays a key role in improving efficiency through the data analysis, performance trackings, and the smart energies management system. Finally, Amperterra represent to push forward the next generation energy solution, which is mostly energy mix, integrating advanced battery storage, green hydrogen supplying, smart grid, and the digital innovations to stabilize and modernize the power supply. And together, this initiative from the backbone of South Africa's future's energy strategies. So I think this is the one that from the right side I want to talk about. And as we can see, the next one is coal, is South Africa energy landscape. You can see the coal actually dominate. We have 82% energy come from the coal. and other energy only about 18%. And the crude oil is only 9%. And then other renewable is, see that the poor renewable energy just 1%. And the energy expenditures is, and the industry is about 44%, and residential is about 19%, and commerce and public service is about 11%, culture is only 3%, and transportation is also 19%, which is quite equivalent to the residentials for the second most energy consumption. And now let me introduce to the green hydrogens. The green hydrogen economies refer to a economy system where green hydrogen produced from renewable energy source, like wind, solar, or hydropower. And I think this is the key definition. What is a green hydrogen? So it needs to be coming from either the wind, solar, or hydropower. So this become a central element in decarbonizing multiple sectors, and this transition to aim to reduce reliance on fossil fuels and minimize the greenhouse gas emission and contribution to the global climate goal. So I think those are the definition, which means green hydrogen. What means green hydrogen? It's the hydrogen that comes from the renewable source. I think this one talk about that. I will go through quickly. So I think this is they talk about different colors. Typically, I only can see most of people talk about gray, blue, and green. Okay, so I think that it's very easy. Gray is the same old time. So we're using the steam, the reforming, okay, and the gasifications, and then we have and the source is the methane or coal, and then the blue is steam reforming, and with the carbon captures about 85 to 95%, and also come from methanes or coal. And turquoise is one that the less to see. Say you use the pyrolysis, so then you use the methanes as the source. And finally, is what we want to achieve is a green hydrogen. So we use the electrolysis, mostly is water splitting, and then using the renewable source for electricity. Okay, so let's give a kind of overview of South Africa's clean energy transitions. Okay, so this actually point introduced the country's shift from the coal-dominated energy system toward renewable and sustainable energy sources such as solar, wind, and hydropower. And the transition and to reduce carbon emissions, improve energy security, and create a more resilient energy infrastructures. And for the green hydrogens and its potentials, and we know that green hydrogens are produced using renewable energy, that's called the green hydrogens, and represent a promising energy carrier for South Africa. With abundant sunlight and the wind resource, the country has the potentials to become a major producer and exporters of green hydrogen, supporting both a domestic, industrial, and global decarbonization effort. And I already talked about a lot about LD, and I like to use this kind of advanced nanotechnologies to produce the catalyst, and because it's with very higher precisions, and so it can create a very new catalyst layer, and then to help the development of the green hydrogen economy. And finally, the scientific and social economic connections. So these sections emphasize the broader impact of these technologies, how scientific innovations and support the economic growth, job creations, and skills development in South Africa. It also highlights the collaboration between the research institution, industry, and government to ensure that the clean energy transition benefit society as a whole. Then the question is, why hydrogen? Why green hydrogens? Okay, so I guess the green hydrogens is generated by splitting waters for electrolysis and into hydrogens and oxygen using the electricity from the renewable sources. So that is the definitions, and such as solar and wind. This process emits no greenhouse gases, making it truly a clean and sustainable energy carrier. And another one is key for decarbonizing industry and transport. Yes, I think that many heavy industries like steel, cement, and the chemicals rely on fossil fuel. Green hydrogen can replace this fuel, significantly reducing carbon emission. It can also power fuel cell vehicle, which is still not very popular. And also that you can think about if you can power fuel cell, the fuel cell generate electricity, can be also using the EV. As I remember that one of the project actually is in China. I'm familiar with is that they're trying to using the liquefied the hydrogens and as the fuel to either fuel the hydrogen car or using this these hydrogens to fuel the fuel cell and to power the EV as well. So I think those are the very interesting propositions from the Chinese and the company. And also the one good thing is enable long-term energy storage. Unlike electricity, hydrogen can be stored for long periods of time and used when renewable generation is low. So this helps balance the grid and ensure the reliable continuous energy supply and essential features for large-scale renewable systems. And actually, this is one thing. So I think that recently there is the Nature papers, okay, and talk about what green hydrogens can be used in the what kind of industry. So it's actually they say that it can decarbonize the hard to abate sectors such as steel, cement, aviation, or shipping, and etc. But the thing is that I think that we actually counter. There is actually the paper we counter with this comment because they say that it's very limited. But I think that also one thing is very important is I think that the paper itself. This is what my strong comment. The paper itself is good paper for the nature paper, but they focus on the northern hemisphere. It's not in the southern hemisphere. Okay, so the difference in the northern hemisphere, they're highly industrialized. So I guess the best things when you get the solar, get the wind or get something, the energies is those kind of energy you can go directly to the production or the industry. So but you know the northern hemisphere is highly industrialized. So that is the most efficient way to get your renewable energy directly into the industrial sectors. But in south hemisphere is different because our industry is not that industrialized. So a lot of energy, and then we also abundant of the solar and the wind energy. So most of the energy you need to try to figure out a way to store. And I think this comes to play a very important role for the hydrogen, because hydrogen, you can use this energy to generate the green hydrogen and you store it. Okay, and then this one can be used as export to the especially northern hemisphere. So, but that is one thing to counter their response and publish in the International Journal of Hydrogen Energies. And finally is support the export and job creation. So I think that's what I just say. We have abundant renewable energy resource. So position us to a potential exporter of green hydrogens and related technology. So I think those are the thing is that can create a job. Okay, that is the one thing always South Africa want to have a job, because we also it's a highly unemployment rate. And okay, so the green hydrogens is I say this is a diagram I like. So you can see from the left side is renewable electricity. Okay, the solar and wind, that's the typical. And you go to the electricity to an electrolyzer. Okay, and then the electrolyzer just water splitting, and then the distribution, you storage, and then you distribution to the transportation or go to the industry, and that is provided zero emission. And then the why hydrogen is a good fuel. Well, I think that this just tell you that hydrogen has a very bad volume energy density, but a good mass energy density, but you need to condense it. So hydrogen has a good mass energy density, but a relatively poor volume energy density and require extreme storage condition, making it expensive to store. But I think this way I like hydrogen. Other party trick is that it burns cleanly, producing only waters and no greenhouse gases. So I think that's the one good part. And this one actually will quickly go through it. I think I talk over time. This renewable energy. So we typically this is just to tell you that renewable energies, solar, wind, hydro, and then you optimize and stability for electrolysis and hydrogen generation via electrolyzers, and then so using the PEN or the alkaline or solid oxide, and also AEM or something, and then the study the catalyst efficiency and durability and cost effectiveness, and monitor hydrogen production rate and energy efficiency, and then do the purifications, and then the compressed hydrogen for storage. Okay, so I think that's 350 to 700 bar is this is typically the one of the hydrogen storage, but I think that there's a lot of different development of hydrogen storage. So you can liquefy it or metal hydrides materials, or you can using the chemical like chemicals carriers. So I think those are a lot of works and doing this hydrogen storage. I think the one key part of what we talk about hydrogen generations. So I think that alkaline PEN and alkaline PEN is kind of like in the forefront already, but it's still expensive. That another problem is expensive, but it's already been able to create hydrogen. I think the biggest problem is the storage, and using liquefied hydrogen is expensive. And then I know that you have to compress, and you have the minus 252.8 degrees to liquefy it. It just doesn't. That just make. Then also once you store, of course, then it's going to be quickly. They have a lot of loss. Okay, there are a lot of loss of the energy. So I think that then we perform the testing and integrations, and finally we can using the data analysis to optimize the usage of the hydrogen. Okay, so I think the challenge in hydrogen technology, the first one is I just say very high electrolyzer cost. So I think the device that split water into hydrogens and oxygens remain very expensive to produce and operate. The cost of materials, manufacturing, maintenance significantly affect the overall price of green hydrogen, making it less competitive with fossil fuel. I will show the data. And also catalyst degradations. Okay, catalysts which speed up the electrolysis reactions often degrade over time due to heat, impurity, and chemical stress. This reduces the system performance and increase the operational cost, highlighting the need for more durable and cost-effective catalyst materials. And another one is storage and transportation limit. So I think that the hydrogen is very light. So the way to do is to compress. You are going to compress high pressures, or you liquefy it, or you transform to the green ammonia. Okay, so I think that, but all this require a lot of energy input for you to really can store. And then also the efficiency losses, and so the energy is lost at the multiple stage during the electrolysis, compressions, storage, and reconvergence into the electricity or fuel. So these are all the location that you have on energy loss. So these efficient losses reduce the overall sustainability and economic viabilities of hydrogen's technology. So I think those are a lot of challenges are still ahead of us. And South Africa and South Africa's potentials and government initiatives. So I guess there is a hydrogen society roadmap, and everybody knows that. Actually, I participate some part of a hydrogen society roadmap. Okay, so I think that's one thing. I think I just assume that all you guys know this roadmap, and we try to collaborating with global partner and local stakeholders. I would say that this part we are not doing very well. Okay, especially the global partner. And one advantage for the critical materials for the for the entire hydrogen value chain. So I think the right side, you can see that the materials, all these PGM group materials, South Africa has nearly have all of them, kind of like a US, kind of like a China rare earth materials. So I think those are the things. This is very important. Platinum, iridium, and the rubidium, and right, and then all these materials is the PGM groups, and all this can be used for water splitting, hydrogen generation, hydrogen transport and storage, and also the hydrogen utilization. So I guess this is a biggest advantage for the South Africa. And this one, I think we heard a lot. And the hydrogen valleys, objective is to kickstart a South African hydrogen economy through the creation of hydrogen valley, kind of like a Silicon Valley. And I hope this is successful, because the thing is, the Silicon Valley, and actually my son is actually in Silicon Valley. But the thing is, this has to be really put into the practice. And oh, wait a minute. And then actually there are three hubs. One is the Mogalakwena and Johannesburg, and then the Durban hub. We are going to introduce that a little bit. Actually, there is one is a catalytic projects, industrial cluster, and demonstrations zone. So I think that today is still the same old one, is we are creating a lot of polluted air. And then the actually is from 2021 to 2050, and we are going to reduce all this the mercury particulate materials matters, and the NOx and SOx, and then and provide a better clean air. But this will be complete by 2050. So after, and then the last one is tomorrow. So I think that's what we say, 2030. And then we're using the renewable energies, and we'll capture the particulate matters, and we can create clean energy or other mercuries, and then the NOx and SOx and CO2 can become a fertilizer. I think that this is one of the developing a hydrogen economy has become a strategic priority for the South Africas. So I think the hydrogen provides a significant opportunity for economic development in South Africa. I think that as a supporter, I think that we should do it with this. So hopefully then we can boost the economic activities and job creation. And especially in this year's State of the Nation address by President Ramaphosa, cite the hydrogen fuel cell as an alternate energy source as a national priorities. And then the hydrogen is contributed to the South Africa's decarbonization objectives and green targets for the sector's level, so can reduce the carbon emission with a net zero target by 2050. Okay, so here actually, while the backbone of strategy is IRRP, hydrogen serve as a vehicle to leverage the new green renewable energy sources and decarbonize the hard to abate sector. So hard to abate sector is important. And then the global commitment toward the hydrogens create an opportunity for South Africa to engage in energy export at the international level. So I think those are the things that we have these hydrogen valleys, and that can with these three hubs, we can produce the sufficient export and to enhance the economy and create a new job. Okay, so I think that this is 1, 2, 3, 4, so many things. I think that I'm not going to talk too much. I already talked too much. So I guess that there is a lot of initiative, okay, and then already been there. And so I guess this is all the things that we need to achieve by the 2030 or and beyond. So I guess this is a lot of for example, number 4, the Hydrogen Valley has a strong potential to contribute to the just energy transitions, and could potentially add 3.9 to 8.8 billion USD to the GDP. And by 2050, while also creating a total about 14,000 to 30,000 jobs per year. Actually, this is less than the other major like the United States. I will show you later. So I think those are the, I'm not going to go through it, and you probably can go through that. But I think that another thing is the hydrogen's levelized cost of hydrogen still pretty high. For the South Africa, it's about $4. So it's compared to the $2, about $2 of gray energy, that's also a problematic. Okay, so I think this shows that 3 hubs. One is the Limpopo and Mogalakwena Limpopo hub, and another Johannesburg hub, and also the Durban and Richards Bay hub. And you can see from here, from the right side, actually it can produce, that is a high and low. So I think that in 2030, and then they can produce, for example, the Johannesburg hub can produce about 74 kiloton of hydrogen per year, and the low is about 41. So you can see this 3 hub is going to be in a lot of the different, from industry, from mobilities, from mining, and from the building. So I think those are the 3 hubs will be able to produce those kind of kilotons of the hydrogens as for the export. And then as I said to you before, levelized cost of hydrogen production is still very expensive. Even go to now it's 2025, and then until 2030. So it's about the $6.1 compared to $2.2 for the gray energies, and then from the Johannesburg. And that pretty much is about the 6.1, 5.5, 5.8. So, and compared to about $2. So still 3 times more expensive, and which is not feasible for really replacing that. And then in 2030 is trying to achieve the goal 4.7 and 5.0 and 4.9, still pretty high. So if you look at this number, and this actually give location 1 is the Johannesburg. So you can see that the green is still quite expensive, even in the 2030, if we can achieve that goal. So, but I think those are the things. Just tell you is we still need to do more to achieve the goal. And this one is actually based on the analysis for the electricity price. If we $65 per million watt hours, so that's mean about 0.65 degree, 0.65 US dollar per degree, and then another one is $0.2 per degree. So based on this, and then also for the electrolyzer cost is a 307 per kilowatt, or 130 kilowatt per 5 tegawatt the installed capacity. So based on this, is that would depend on your total electricity price, will show the quite difference. So if we can have electricity price drop to about 0.2, and then we have the chance to reach the fossil fuel range. Okay, because fossil fuel will keep increasing the price. So the challenge in scaling the green hydrogen in South Africa, the challenge of scaling green hydrogens is a lot. There's a lot of challenges. Production is highlighted by the electrolysis technology promising status and logistical hurdle of matching supply with growing demand. One thing is that one thing I'd like to show you, but this is data a little bit old, but thing is this is the data actually I received very recently. If you look at this, I couldn't find the South Africa. Did anyone can find the South Africa? I couldn't find the South Africa. So that's what I mean. Looks like we don't have a lot of international cooperative agreement. If correct me if I'm wrong, because this is only to 2022. But when I see this data, I'm kind of shocked. Where is the South Africa? So I guess that we need to kind of see whether we can specialize in some major energy country like China, like the US. And so I think that we need to figure out the way to really work to the international project. Correct me if I'm wrong, okay? That's the data I have. Technological challenges for the electrolyzers. So this shows the two major different electrolyzer, alkaline PEN and excuse me, and AEN and solid oxide. So I guess that the currently electrolyzer stack is about 2 to 5 megawatt and planned for the 20 megawatt. Actually, I went to China. Actually, they already have a 50 megawatt. I see one demonstration. So I think those are in the development. So 50 megawatt. And but electrolyzer technology is not mature enough that and there are different technology options under development with no clear winner at this stage. So I think that we need actually is a gigawatt, but I think that for you can see 20 megawatt is far away from the gigawatt. So I think that if it's the trend that can develop the gigawatt, the electrolyzers. So I think those are the things we are aiming at too. So
sorry, Prof. Jen. Just that we've gone quite a lot into the extra time.
Okay.
I'll just give you some time, yeah, because the delegates would have sustained their time, yeah.
Let me finish it 2 minutes, okay? Let me finish it.
Sorry, you can just wrap up and take about a few minutes, right?
Okay, so I think this is a global hub. I think that I'm not going to talk too much, but the thing is we need to build an electrolyzer park. We need to have a desalination plant, and then the green ammonia production plant, because once we have a green hydrogens, we can produce a green ammonia. And we have the storage facility, and also the solar wind and battery park, and also supply park for the key common materials, and then the gigawatt factory. So which one will make us lead in the world? And this is one thing I just talked about. US actually has a 7 hub, and they invest about the $7 billion US. And I don't know how much South Africa is investment, but they already set up the 7 I think the 7 hub, and the total is about they can provide about the more than I think it's more than how many I think it's more than about 300,000 job for them. And then this is another one. I think that Germany, and they have provided 9 billion euros. Okay, 9 billion euro, which is much more than the United States. And Germany only is not like the entire United States. So United States is not as good as Germany. But Germany will invest a lot of funding to this. Actually, it's a lot of project. Actually, we will talk about that. We have one project starting with the leader is from Germany. And this is, I think that for the 1 gigawatt, the green hydrogen plant based on AWE technology, alkaline water electrolyzers technologies. And this is actually one I like. Is this Hydrox developed this technology, so they have the hydrogens, they have the electricity and the carbon dioxide. So this is a really nice demonstration of how the electrolyzers play into the role of the green hydrogen. And this is another one. I look at the 1 day of the instant the satellite image. This shows all the cargos, okay, in the world in the 1 instant of the one instant of time. And then this is the airplane. So if we can utilize a certain portion of this this kind of transportation using the hydrogens, and then there is a huge market we can use. That's what I kind of look at this. And okay, so I think that's my publication. So it's somewhat not as new. And actually, I just want to talk about that. We are the partner in the DAAD call for the African German Center JET, Just Energy Transition South Africa Energize Program, which is about 6.5 million euro has been awarded. Unfortunately, we are not the leading, so we only get the small chunk of money. So, and we are also developing the Euro Horizon proposals of green hydrogens on improving the performance of low temperature electrolyzers. And unfortunately, this year we didn't get it, but we are going to come again next year. I really welcome all the people, potential in South Africa can work with us, and then we can develop a strong proposal. I know that this needs a lot of international partner, and we do have a lot of international partner. And there's another one is EOI for the hub to host the presidential PhD program in just energy transition, which is currently under review. And then another one is implementation partner for the green hydrogen centers of specializations, GHCOS, which is also under review. Okay, thank you very much. So I think I talked way too much. I'm wasting too much time. Sorry about that. And then this is my last slide. Thank you. And then so why don't you do?
Thank you, Prof. Jen. Your talk was so interesting that thank you, Prof. Jen.
Okay.
Your talk was very interesting, so I just let you go on, but we had to stop at the end because of the delegates. Yeah, no, but it was really very interesting, so I did let you go on. And yeah, very interesting. I think you gave us both the technical and the government side of it, and then the global picture also. So I think the delegates, the attendees will really value your information and your presentation. And so I think everybody knows where Prof. Jen is. He is at the University of Johannesburg, and I know we will make some time for a few questions. And Prof. Jen, if you could just answer the two in the Q&A box, I will allow now Mr. Dave Wright will now take over. We will maybe about 15 minutes or so for Q&A. But if Prof. Jen could just answer the two questions in the Q&A box, and then Prof. Dave Wright will take over, and we will have a Q&A section. But just to go back to say, Prof. Jen is at UJ. He is given a lot of information, and the recording would be on Facebook. So I'm sure you will all be welcome to contact him for information or any further collaboration. I now hand you over to Prof. Dave Wright. And we, as I said, time is a bit short, but we will try and do some discussion. So I'll hand you over to Prof. Dave Wright.
Thanks, Maggie. Prof. Jen, I'm not sure if you've got the two, well, there are actually three questions that are now in the Q&A.
Yes.
Have you seen them?
Yes, I see that.
Can you perhaps just respond to each of them as they come up?
Let me answer the first questions. I think the first question is a very, very good questions. Oh, sorry. So is that the? Oh, I can answer, right? Yeah. Where is it? Oh.
Dave, do you want him to do it live or to type it up?
This one, I have questions for me, and it's can AI ML machine learning predict the optimal ALB recipe, precursor, temperatures, pulse, and for desired film properties. Actually, this is a really, really good questions. Actually, I have one entire team actually is working in the machine learning. And this actually, so I guess actually there is I have a collaboration with Harbin Institute Technologies, and then actually they use the AI and the machine learning to do some optimal ALD recipe the prediction. The result is because they they need a lot of data, but unfortunately, this data is not available currently. And so I guess this is the one that they use limited data, but they create very good machine learning models, and then they can predict. But I guess that they can predict certain process is very good, but it's not the overall. But I think this is the way to go to how you're going to deposit the optimal ALD recipe. Yes, this is the one. If you are interested, I don't know who is this one. If this is a student or something? I don't know. If you're a student, and you're welcome to come to my research group, and we are actually really working on that. Actually, this is a really good question. Actually, in the future, this is going to the futures.
And your response to the second question about making perovskites using ALD?
Where?
The second question is, can we make perovskites using ALD?
Well, I think that we haven't do that yet. So I think that part I cannot answer that right now, and because we didn't use we haven't deposited the perovskites the process for the solar cell. So perovskite solar cell, we are just in the process. We are not developing that yet. So
thanks, Prof. And then the last question that we've got on the Q&A is potential collaboration in the BRICS countries on green hydrogen. Have you got a comment on that, perhaps?
Yeah, we have. I think that again, I'm working with China. Okay, especially in the actually we just have built the centers, the South Africa's which is us UJ. And China is Shandong University, and that actually is one of the major portion is the green hydrogens. So we working with the China, and China actually is China is one of the BRICS country, the biggest BRICS country. So we do with the China, and also I have a certain connection with the India, and then they want to work with us with this green hydrogen. So I think those are yes, I would say yes. Yeah.
Great. Thanks very much indeed, Prof. Those are all the questions that we have on the Q&A. So given the time factor, Maggie, I wonder whether we shouldn't just move to closing remarks.
Okay, all that time is.
Okay, I think that's fine. If anybody else has any other questions, you're welcome to put it on the Q&A. And as I did say, Prof is at UJ, and he would respond if you do try and contact him. I would now thank you, Dave. To start, thank you, Prof. Jen. As I said, your talk was so interesting, so I did let you go on. But I'm sure we are going to bring you back next year, and
Sure.
maybe you can take us a little bit further into maybe the scaling up or something else, and maybe tell us what's happening in the hydrogen space nationally, and how South Africa maybe have progressed. So thank you on behalf of the Academy of Sciences, Academy of Engineering, the SAIChE, and Institute of Electrical Engineers. We thank you for agreeing to do the webinar for us. To all the delegates, thank you for all of you for registering and supporting us. I hope that you also spread the word, and that more people are now becoming aware of what's happening in the hydrogen space. So we will try to bring you more. I'm not sure about this year, but maybe next year. And to the organizers, Rajeshri Mahabir, thanks to Dave Wright, Henrietta Wagner, and I did mention all the hosts. I would like to thank everybody again for making this a success, and we look forward to seeing you all at future webinars. So have a good evening and take care. Goodbye.
Thank you. Thank you, everybody, and goodbye.
Goodbye, Prof. Jen.
Thanks, Maggie. Cheerio.
Thank you.
Bye, everyone.
Bye, Dave. Bye.